Okay, thank you. I just stopped the timer because I have too many slides. You can look at them at your leisure. Okay, well, thank you. Thank you, Tobias. He's also part of this project. I'm helped in this talk with the slides by Patrick Fuhrmann, who's the coordinator of ExPaNDS. And I hope to explain to you what PaNOSC and ExPaNDS have achieved and where we're going to from now. You'll notice that the pretty slides are by Patrick and the more basic slides are by me. So the talk outline will be a very quick overview of what PaNOSC and ExPaNDS are, what they've achieved, what is a data commons in case you don't know what it is or how we define it, how could we build it, why would we build it, and how could we maybe sustain it. That'll be the shortest part, how we sustain it. But we can have, it's only 15 minutes, we can't go very far into this, but we can discuss this afterwards. And what is your role in the data commons? Because we need you. So very quick cheat sheet of what these two projects were. First one was PaNOSC. I coordinate that with a lot of other people. Started in December 2018. So it's ending in 2 months' time. I'll be a free man in 2 months' time. And ExPaNDS started 6 months later. And thanks to COVID, got a 6 months extension. So they almost finished at the same time. The amount of funding is less for ExPaNDS, but there are more people, so they could do more. And the amount of funding for the S3s was quite consistent. You find all the source code, or a lot of the source code here, and you have all the usual social medias as well as the websites, which contain quite a lot of information. The partners in these, in case you missed that in that last slide, are basically all of you as well. I mean, all your facilities. So if we separate it into photons and neutrons, it's almost all of the LEAPS partners, and then only a few of the neutrons are missing, but that was a decision of the facility. So a very good representation, and we had two institutes joining us, ELI, which is a coming up institute in Eastern Europe or Central Europe, and CERIC as well, which is in Central Europe. We did a lot of stuff. We also, as it's also nice to still see Robert still amongst us, because I remember Robert from many years ago. We started working on this stuff that we're talking about now already in 2010, if not 2018. So it's a long haul, whereas Robert justly pointed out, we've been working on PaN data ODI, PaN data Europe, all of these EU projects have always brought us together in this space, data management. And the results you can see down here, which I'll go a little bit more into detail. And the binding factor today, which goes beyond the photons and neutrons, is the European Open Science Grant. So that's where we're heading. So yes, the 10 primary outcomes, I thought I'd just take these one by one, is the data policy, which is very important if you want to be able to open up the data and share it. The data management plans have also become important. There are many funders who insist on them now. And for instance, at ESRF, we've just rolled out data management plans for all proposals, but on a voluntary basis. So we fill them out for them, and then they can use them. FAIR is very much more complicated than it looks like if you're just starting off on FAIR. And so you need to invest a lot of time. Robert pointed that out already. We're very happy to see almost everyone mention Nexus HDF5 here. So this has become a no-brainer. It still requires efforts, and I think we have to continue with that. But these two projects also pushed this a lot. The federated search, which I will talk about more, and the open data portal, that's actually the core of some of the slides coming up. We have an AAI, which will be the first official European Open Science Cloud AAI. Probably none of you are using it, but you might end up using it one day. Yeah, you can use it already in quite a number of facilities. Jupyter Lab, we had a very strong push to push generic tools like Jupyter Lab, and I think we've seen now everyone's adopted it. It wasn't invented by these projects, but we promoted it a lot, and you saw the tools that the tool that Loic presented is also an example of how we supported the ecosystem of Jupyter Lab, and also displaying Nexus files. the Visa portal, which was for remote data analysis. We heard of an alternative from Emmanuel, but this is the kind of service that you need, and there was one which was provided. There was a lot of simulation also done as part of this project, and this has come out. Some of them, two of the most, let's say, the de facto standards for simulating beams on neutrons, MaxTAS and OASIS for photons, were part of this project. So they also, again, feeding back into the community. And the PaN learning program and platform, which Andrew spoke about at the end of yesterday's session. So all of these things came out of these projects, and I think it was quite a good show that we managed to produce quite a lot of stuff, and it's all been heading towards something which I'm now going to call the PaN Data Commons. But just to say that also these are part of the bricks of open science. So open science is made up. The definition of open science nowadays is accepted to be these 6 areas in which you have to share data, your source code, methodologies, learning material, open access to publications. And the 4 of them we could support. We provided and helped supporting open science in that sense. And just for your interest, some of the facilities are moving towards having an open science policy, which is quite an interesting challenge as well. So yes, Andrew did mention this yesterday. We have one common goal, but I now use the past tense. We had one common goal. We now have a new goal because these projects are coming to an end. What we've achieved is something getting closer towards fair data, but we need a new goal to continue. And I think the new goal is to build on top of this and create a commons of that. So what is a commons? So commons, if you look it up in Wikipedia or in your favorite dictionary, is something that's there's a common. It was used in the UK, first of all, for land, but it's something which is owned by the collective. When the collective could be the entire world, it could be a community. It's not a private property anymore. And when you want to set up a commons, you've got a lot of things you have to set up, at least for data. Is you need infrastructure, you need data formats, metadata. You need practices, policies, and then you also need you guys, the people, the scientists. And I thought this just summed up all of these layers that you need to build up a commons. You can't just say, well, here's my data. And there's also some very good articles out there if you're interested to know more about this. I found this article by Open Future from this summer. They had a very nice summary of it. There's also the NIH is pushing this, and even Google is pushing this. So I think this statement is quite accurate. Data Commons aggregates data from a wide range of sources into a unified database to make it more accessible and useful. So the idea would be to add value to the existing data. Of course, we have to make it visible. An example of the commons we already saw on Tuesday, I think it was, or was it Wednesday, by Marco Scheidken, who presented Nomad for material science. So this is very close to what a commons is, or this is a commons, but for material science. And what we're looking at is a commons which will go much over everything that all the data that's produced. Yeah. And there's also a commons, of course, if it's a good idea, usually Google's picked it up. Google has a data commons. They even own this address, datacommons.org. But we thought at one point Google was there to help us. And we had this, I don't know if you know about the Google dataset search, which is was actually supposed to help us to find data. And I just tested it before I came here again. It doesn't really help you because it's too broad. And so even if you put your markup in there, I don't think the users will use this so much, or we won't be able to find the data we're looking for on the Google dataset search. It's just too broad. There's probably other areas which people will find something. And he has another very good example, which is a genomic data commons, which recently had a visit from Joe Biden, who said, I can't tell you how excited I am about this. And I'm hoping in 1 month's time, I've made a similar presentation to the Leaps plenary, and I'm hoping the people there will say the same thing, but I'm not holding my breath on that. And there's an example that we had also from the EOSRF, which I recommend looking at, is this one for the Human Organ Atlas, and which is a project to scan the entire human body at the cellular level, but down from the macro level. And this has spun off already. You can just see after less than a year, this is already spun off into private companies that are using this. They're also working with doctors on the data that's out there, the open data. And it's been picked up by the next issue. This is a classic text for anatomy for students called Grey's Anatomy. It's not the TV show. And this is going to use the renderings of this data as the pictures in the next Grey's Anatomy. Yeah? So just to show that data spawns off other things that we didn't even dream of, maybe. Why would we have a data common? So I thought I'd continue in the analogy that Dion started, which was in Africa. This is in Johannesburg. You have these gold mines, which were there from the last century, and they produce these huge dumps, these mine dumps there. And if you look at a picture, aerial picture, you see lots of these mine dumps. And depending on the price of gold, people go back in there and they mine the mine dumps to still get gold out of it. And well, we could say this is a bit like the data. If we just, it actually can have value depending on what is the science that's being done. We could actually reuse the data. I wouldn't take this analogy too far because these mine dumps also have pollution. They're quite polluted. They have radioactive materials in there. So we won't say your data is polluted. Yeah? But if we speak about pollution, I thought this was, and something I always wanted to try, and I've tried to do it with this. So those of you who live in Europe, you probably experienced this very hot summer. This is the data from the summer of 2022. And if you were living either in this part or the UK, they broke all their records, apparently. They went over 40 degrees. And in France, well, we actually felt the heat for 2 months, Germany as well. If you were in Norway, you were probably not too hot, but you can see the global warming effect is becoming clearer and clearer. And so what I thought we could do, and even this is an article which came out on Tuesday about from Caterina Biscari from Alba, saying that the cost of electricity will maybe make them shut down the facility. And if we then think that we will be running the facility for a smaller fraction of the time now, maybe we should make more out of the data that we have. Yeah? And so what I thought we could do is try and calculate the carbon footprint of an experiment. So this is an attempt, and I've tried to find as much data as I could to see how we could estimate this, because calculating carbon footprint is quite difficult. There's so many factors involved, so many things, everything that's produced before you start what you want to calculate and how does that influence it. But, so this is an estimate. But what I did is I took, imagine 3 users flying from Copenhagen to Grenoble. They would take the flight, which is 380 kilograms of CO2 equivalent, and the bus would take 10 kilograms as well. Then if we take a beam time at USRF, we have an 8 megawatt consumption when we running the beam. So if we say between 40 or 45 beam lines that are running at a time, I took 42 because that's a nice number. We say that 1/42 of that energy was used for that experiment for 1 week. Storing data on disk, I assumed 100 gigabytes, processing 1 week on a 64-core machine, full time, and transferring the data back to the cloud. All of the numbers that I've come up for you, I put links at the end so you can go and check them. And if you take the electricity mix that we have in France at the moment, you can actually follow this online. This is from Monday. It shows what the CO2 equivalent is for the current energy mix on Monday. So I took the high value because in France we have nuclear energy, but I'm not sure this is the company running the plants. I'm not sure that this value is probably, maybe they've been optimistic because it's a very low value, I think, compared to other energies, if you take coal and so on, but it's 75 grams per kilowatt hour. And if you put all those numbers in there, an experiment of 1 week would produce or would require the equivalent of more than 3 tons of CO2. And this is obviously the main component of this is the beam time, because the facility uses so much energy. But if we say we're trying to, as humans, to get down to 5 tons per year, this obviously means that the data has then become something which has cost a lot of CO2. And so we should be using this data more. So, if you think of what is a ton of CO2, it's the size of a house. So an experiment, I don't know how big this hall is here, but it would be 30 meters cubed, It's probably bigger than this auditorium. Yeah. So that's another reason why we should be storing the data, because if you store that data on tape for a long time, tape is a much smaller fraction of energy. Most of it's switched off all the time, and it would only be the equivalent. So we could keep this data for 10 years for roughly 7 kilograms of CO2. So it makes a case for keeping and making the most out of our data. And that's sort of the vision behind the data commons. I won't be able to go into this too much, but the main idea is to provide the data, but as you saw from these projects, we're also providing the tools around it. Of course, there would be remote access as well. This is the canonical picture I show, where we actually leave the data in the facilities. This is already the case with what's called the PaN Open Data Portal. And we have a federated search on top of this. And connected today, we already have ESS, PSI. No, I think PSI is half connected or full. Yeah, almost there. ILL, MAX4, CERIC, and ESOH. And ILL is also almost there. So by the end of this project in November, we'll have all of these on board. And how it works, you can go and try it out yourself, is you just go to PaN data, you go to data.panos.eu, and you can search for things. This is still not at the perfect stage where I'd say I'd like to give this to all our users, but the concepts are there already, and they were very well presented on Tuesday by Max. Max is sitting up there. This is just Max's poster, which I don't know if you all had a chance to see, but you can look at it again. It explains how the portal puts in the data and then sends the request out to all the facilities, and then sends back the results, and you can refine them as well. And the implementation for SciCat, which is also now widely used, metadata catalog, is explained in full detail here. So we already have the bricks for that. What we need from you is that first of all, you have to have a data repository. Yeah? So I don't know, I think everyone is on the way to getting there, even if you have a little bit of data. Deploy this search API as well as the scoring, connected, or just contact Max. Max can help you connect it up together. We need data stewards. For sure, the quality of the data will depend a lot on what effort people put into the metadata. And then train scientists. Yeah? We have a training platform as well, but train scientists in the meaning of what is needed. Once we have all of this, one of the things that Google is pushing, but I think we could also do as well, is you can then create additional data or more information by linking up the data that's there. So finding all of the paleontology, all of the human life sciences data, or things that are similar. So I will conclude with that. I think we've put everything, the foundations are there, and we're actually quite far. Of course, it's a constant effort. You can't just stop now. We want to carry on with this, and one of the places where we will look for funding, but it's highly likely we will get funding for this if we go that way, is at the EOSC. So the EOSC is providing some funding for this. And yes, I think we can become, just like the astronomers, just like the life sciences, genomics, we can become a source of fair data. And I don't know if you remember, I did say we need you. Yeah. Okay, that's it. Thank you, Andy. And for those who want to check the calculations, I don't have it here. I should, I'll upload it. They're all the links where you can check the calculations.
Very nice talk, as usual. So I see that you have shown Google dataset as an example of a broad search engine. But the EOSC also has put in place its own search engine for science, like B2Find and Google. Just wanted to know what's your opinion on that. Should we help them develop, or should we really focus on PaN?
This is I have the expert next to me, so I have to be careful.
Yeah.
No, but I think
you're within arm's length, so it's okay.
No, I think we did also connect all of our during PaNOSC and ExPaNDS to B2Find. So we did this effort to expose the metadata. But similar to Google dataset search, I think these very broad search machines are not focused enough. So you can't, and that we always said we wanted to have a search machine which allowed us to go into our domain, yeah? So that we can have more parameters which are specific to our domain. So I think we should link to them. We linked also to Google Dataset Search, but it's not enough.
Okay, thank you very much, Andy. More discussions in the coffee break.
Okay, thank you.